Hello, everybody. Welcome back to another video after quite a while. I've had tons of requests to make videos on questions. I received an email from someone who watches my videos, and they gave me a set of questions which they would like me to make videos on. Now, of course, there were quite a bit of questions in those, and all of them were related to the HL part of organic chemistry, which is things to do with SN1, SN2 substitution, to do with reduction of organic molecules, to do with optical isomerism. So now I've gone through that and I've sort of picked out two questions which I think have like a repeated theme in the questions, right? So like if you watch this video and if you learn these two concepts that I'm going to teach you, you will be able to answer most, if not all, the type of questions that are shown relating to the HL organic chemistry questions. So let's get on to it. I will also make a second video where I take a look at a few more questions, more to do with the reduction of organic molecules. And I think these two videos combined should give you a good idea of how to tackle these questions. But let's get on to it. So over here, we have our first question, which asks us, which molecule exhibits optical isomerism? Now, in that worksheet that I was given, and I think it was an IB question bank worksheet, this type of question came up at least 10, 15 times, right? It was pretty common, and each time they gave you a different set of substances or molecules, and I'm going to show you how to figure out, well, which molecule is optically active. Now, the first thing I want you to do is I want you to just draw them out quickly, right? I know in MCQs you don't have much time, right? You have a minute maximum to do the questions, but I would suggest that this is a question that you spend a little more time on, right? Because some questions are maybe require 10 seconds for you to solve. But this one, I would recommend you to take a bit of time with it because you can easily slip up under the pressure. So let's see how I would do this. So I'm just going to start with A. I'm going to draw A out. So it's a pentane, so that means it contains 5 carbons. I'm just going to draw the 5 carbons first. Okay, that's 5 carbons. And it says 3-chloropentane. That means the chlorine, so it's a halogenoalkane, and the chlorine is located on the 3rd carbon. So that would be this carbon. And I'm not going to fill out the hydrogens. I think you get the idea. I'm just going to draw these ones. Right. Now, is this a chiral molecule, right? If you want your molecule to be optically active or to display optical isomerism, it needs to have a chiral center. I should have probably started off with what this is. My apologies for that, but I think I'll explain it now. So this is a chiral center. If you want your molecule to display optical isomerism, a chiral center must exist. And what is a chiral center? A chiral center is basically a carbon molecule. Well, this is the definition for IB. In college, it gets a bit more complicated, but you don't have to worry about that right now. So a chiral center is basically a carbon molecule which has 4 different groups attached to it. So it would have something like maybe this. Something like this maybe. So this carbon is considered as a chiral center because it has 4 different groups attached to it. All of these groups are different from one another. This, however, this is not a chiral center because these 2 groups are the same. And the requirement for a molecule to display optical isomerism, is for it to have a chiral center. And a chiral center, by definition, means that the carbon, a carbon molecule in the particular substance should display isomerism, or should have 4 different groups attached to it. Words are a bit of a difficulty today for me. I'm quite tired, but hopefully I'm not confusing you too much. If you would like a better explanation of what a chiral center is, please go and watch my earlier video where I think I do a better job at explaining it today. Today, words are just not happening for me. So anyways, let's look at this molecule. Does a chiral center exist? So I'm going to start off with the first carbon. Well, does it have four different groups attached to it? Well, no, because it has three hydrogens actually. So no, this is not chiral. This carbon is not chiral. Let's look at this carbon. Does it have four different groups attached to it? Well, no, it has two hydrogens, which are the same. So no, this is not chiral as well. Let's look at the next carbon. Well, this carbon has one chlorine and one hydrogen, and it has these two groups attached to it on the sides, right? This part and this part. And what are these parts? Well, it's C2H5 and it's C2H5. So it actually looks something like this. I've just condensed this molecule into a smaller part. So this molecule, I've just condensed it into this. And well, is this chiral? No, it cannot be chiral because the carbon has two of the same groups attached to it. So no, this carbon is not chiral either. And because this side is the same as this side, these two carbons are not going to be chiral either, meaning that this whole molecule does not have any chiral centers in it. And that means that it cannot exhibit optical isomerism. So A is out of our options. Now, I'm just going to put a quick thing over here so that you find it a bit easy. If chiral center is equal to optical isomerism. If it has a chiral center, it will display optical isomerism. That is very simple. That is the little mantra, if you may. So if you remember that, you will be able to solve these questions pretty easily. Now let's look at the next molecule. It's 2-chlorobutane, B, 2-chlorobutane. So butane, meaning it has 4 carbons. 1, 2, 3, 4. That's butane. And 2-chlorobutane, that means the chlorine is located on the second carbon. And well, the rest are just hydrogens. So I'm not going to draw all of them out. Just going to put these lines. Now, is this molecule chiral? Let's take a look. Let's take a look. So, well, this carbon over here is definitely not going to be chiral because, well, it has 3 hydrogens attached to it. Neither is this carbon. It has 2 hydrogens attached to it. What about this carbon? This carbon could actually be chiral, you know. I'm going to condense it down a bit. So this is basically well, would you look at that? This carbon is chiral. It has 1, 2, 3, and 4 different groups attached to it. So this carbon is chiral, and this molecule has a chiral center. That means that it will display optical isomerism. So yes, B is our correct answer. Now, ordinarily in the exam situation, if you find the answer maybe when you've reached the second or the third option. So if you're drawing out your molecules and you find an answer such as B, which makes sense, you can go on. You can select this answer as your correct answer and move on. But if you have extra time in the end, I would always recommend you to come back and draw out the other 2 molecules and make sure they don't have any chiral centers, right? Because that will help you identify if you've made any mistakes or slip-ups. So for that, I'm going to draw out the other 2 molecules as well, and I'm going to show you that they don't have any chiral centers in them. Or maybe they do, and maybe I have made a mistake. Let's see. I'm going to draw out 1,3-dichloropropane. So it's propane. That means it's going to have 3 carbons. Oops, what happened to my pen? It appears to have stopped working. Okay, there it is. It's back. So this is propane. So it's 1,3-dichloropropane. So dichloro meaning there are 2 chlorines, and each of them are on carbon number 1 and carbon number 3. And then the rest are just hydrogens. Well, is this molecule chiral? Well, no, this carbon cannot be chiral because it has 2 hydrogens over here. So nope. What about this carbon? Nope, it has 2 hydrogens. This is not chiral. And same thing for this. This is not chiral because it has 2 hydrogens attached to it. So, well, let's move on to the next part. 1,3-dichloropropane is wrong. This cannot be our answer. And let's look at D. 2-chloro, 2-methyl propane. So again, it's a propane. That means it has 3 carbons. 2-chloro means that there is a chlorine on the second carbon, and 2-methyl means that there is a methyl group on the second carbon as well. And well, the rest are just hydrogens. Can this be chiral? Well, no, this cannot be chiral. This cannot be chiral. Now, this is interesting, right? You may look at this and think, well, this could be chiral 1, 2, 3, 4, right? But again, it's the same case as the first molecule, where the groups up and down, this one and this one, they are both different, but the groups on the side are the same. Both of these are CH3. So automatically, this carbon is not chiral. That means that D is also not correct. So hopefully I've shown you why B is the correct answer and how you can go about approaching this question. I'm going to move on to the next part, which is this. So this would cover sort of SN1 and SN2 reactions, right? Nucleophilic substitutions. So they've asked us which factors affect the rate of nucleophilic substitution in halogenoalkanes. And now we've been given 3 options, and then we have been given A, B, C, and D, where you select 1 and 2, 1 and 3, and I'm sure you've come across these kind of questions. So I'm going to look at each one of these options, and I'm going to deduce whether they are true or not. So let's look at the first part. 1, the nature of the attacking nucleophile. Does this affect the rate of nucleophilic substitution? Well, yes, indeed, it does. This part, the nature of the attacking nucleophile, if you have studied your topic well, you would know that this part is only applicable to SN2 reactions, right? In SN1 reactions, the rate is determined only by the halogenoalkane. So the concentration of the halogenoalkane, I'm so sorry for the handwriting. As in SN1 reactions, the concentration of the halogenoalkane determines the rate. In SN2 reactions, both the attacking nucleophile, I'll just write nucleophile, both the nucleophile and the halogenoalkane determine the rate of reaction. So that's why it's called SN2 reaction. 2, that means 2 factors which are determining the rate, whereas in SN1, only 1 factor determines the rate. Now, why does this happen? Why are SN2 reactions dependent on the nature of the attacking nucleophile? The reason why this happens is because if you look at the type of molecules that undergo an SN2 reaction, and those are primary halogenoalkanes. So remember, primary halogenoalkanes undergo SN2 reactions. So a primary halogenoalkane would look something like this. So this is a primary halogenoalkane. You have, suppose, a nucleophile like this. Now this will come and attack this carbon over here. These electrons will go to chlorine, and soon you'll end up with something looking like this. But this transition from this to this, it requires you to be very fast. This transition needs to happen quickly, because without this chlorine, this carbon is very unstable. When this chlorine leaves, there will be a positive charge over here. And that needs to be filled up quickly. Otherwise, the carbon, or we refer to this as the carbocation, will be very unstable. So the nature of the attacking the nucleophile, this nucleophile that is attacking this carbon should be a very strong nucleophile. Otherwise, this process will not work. And consequently, the nature of the attacking nucleophile does matter. So any option which doesn't have 1 in it, which is C doesn't have 1, it should be eliminated. Let's look at part 2, the identity of the halogen. So this is the halogen. So I've already mentioned that nucleophilic substitution for the IB course, you learn about them with regards to halogenoalkanes. So I'm going to take the same example again, which is chloropropane, right? 1-chloropropane. So does the identity of the halogen matter? Yes, it does. And it actually matters for both SN1 and SN2 reactions. Now, this chlorine is going to leave, right? When this nucleophile shows up, this chlorine is going to be like, okay, bye-bye. I'm going to take both electrons from this and I'm going to dip. And this nucleophile is going to come with its 2 electrons and it's going to give them to the carbon, this carbon over here, right? Now, this chlorine, now particularly in SN1 reactions, right? In SN1 reactions, the leaving group, wait, I'm just going to draw a molecule which undergoes SN1. So this molecule over here will undergo SN1 reaction because this is a secondary halogenoalkane. So in a SN1 reaction, what happens is that unlike an SN2 reaction where both the chlorine leaving and the nucleophile coming happens quickly, in an SN1 reaction, that does not happen quickly. The only part, the part where this chlorine leaves or the halogen leaves is a slow step. And where the nucleophile comes is a fast step. So automatically, the part where this halogen leaves is the rate determining step, right? Because we've learned previously that the slowest step in any reaction is the rate determining step. So if you want your rate of nucleophilic substitution to be fast, you want your halogen or your halogen to be able to leave fast, right? Because in SN1 reactions, that is what's going to determine your rate. And some halogens are better at leaving than others. And how can we tell if one is better than the other? It is very simple. Look at the atomic radius of the atom. So chlorine, for example, has a smaller atomic radius than something like iodine, right? So iodine has a greater atomic radius than chlorine. And that makes it easier for iodine to leave. If an atom has a larger atomic radius, it's going to find it easier to leave than if it has a smaller atomic radius. So automatically, as you go down the halogen periodic table, group 17, as you go down, the ability of the halogen to leave becomes easier. And that means that the identity of the halogen is going to determine how fast your nucleophilic substitution occurs. If you have something like this, right? If you have the same propane, but instead of chlorine, you have an iodine here. This molecule is going to undergo nucleophilic substitution faster than this molecule because iodine is a better leaving group than chlorine because iodine has a larger atomic radius. So hopefully that makes sense. So the identity of the halogen matters. So any option which doesn't have 2 in it can be eliminated. Now we're left with A and D. So number 3, the structure of the halogenoalkane. Does this affect the rate of nucleophilic substitution? Well, yes, absolutely it does. And I think I've showed you how it does, right? If you have a primary halogenoalkane where the chlorine is or the halogen is located on the first carbon, well then the rate of nucleophilic substitution is going to be different. But if you have the halogen located on a secondary or tertiary carbon, then yes, again, the rate is going to be different. So the structure of the halogenoalkane does matter. Therefore, our answer is actually D. Hopefully I've understood, I've explained that well to you, and hopefully you've understood. Thank you so much for watching this video. Please send me your other questions. I will do my best to address them and make videos about them. I hope this video has helped. If you have any other questions, please feel free to reach out to me. I always reply to my messages as soon as I can. And that's it. Thank you so much for watching, and I'll see you in another video with another question. Goodbye.